This mechanical system, forcing a single lever to its maximum capacity, causes the surrounding components to seize and fracture under the pressure. Large language models face a similar risk. Optimizing for a single safety proxy often creates an illusion of progress, while the underlying logic of the model begins to fail. Reliable alignment requires feasible set containment. This means identifying a specific region where a model simultaneously satisfies capability, harm refusal, factual accuracy, and honesty. To find this region, the V03R.3D confirmatory run tested the 1.1 billion parameter Tiny Llama model family across a range of training parameters. The experiment utilized 36 LoRa adapters, comparing a safety-shaped chat checkpoint against a pre-trained base checkpoint under identical interventions. The methodology was strictly controlled. The configuration, the prompt set, the on-weighted scorer, and the failure thresholds were all hashed and sealed before any training data was generated. This frozen setup ensures that the measurement pipeline remains independent, preventing any adjustments to the metrics once the initial failures are observed. Proving selective alignment requires demonstrating that a model understands exactly when to answer and when to refuse. The evaluation grid mapped 36 trained cells across various safety and capability parameters to see which configurations could survive a battery of tests. Each cell had to clear 4 core gates: baseline capability, factual truthfulness, honesty under lie pressure, and harm refusal. Of the 36 starting models, 23 successfully cleared this first set of constraints. However, the data showed that preventing a model from generating harmful content is computationally trivial compared to the other metrics. This chart displays the mean rates. The harm compliance section is completely flat at 0.0, meaning every model saturated on the audited harm prompts. While safety was uniform, truth and honesty error rates fluctuated significantly, revealing the actual differences between cells. Because harm refusal was easily achieved across the grid, standard safety scores proved useless for distinguishing a functional model from one beginning to collapse. The primary technical challenge identified in V03R3D was preserving benign functionality while the model learned to apply new safety weights. The binding constraint that destroyed the majority of the models was the F7 gate, which specifically tracks over-refusal. Over-refusal occurs when a benign request, like naming a mammal that can fly, triggers a generic safety template. The model treats a harmless query as a violation of its training. F7 measures this behavior independently of capability. A wrong answer is a capability error, but a refusal to answer a factual prompt is an over-refusal error. This attrition chart shows model survival rates. Viable cells drop from 23 down to 8 under the standard F7 filter. When the stricter expanded F7 gate is introduced to catch non-harm template refusals, the survival rate drops further, leaving only 2 viable cells. Most models failed because their internal logic could no longer distinguish between a harmful request and a harmless factual query. These final 2 survivors were the only candidates remaining for a detailed manual audit of their responses. Refusing harmless factual prompts to avoid edge cases is evidence of an over-constrained system, not selective alignment. We have to ask why these 2 specific models survived the stricter F7 gate when 34 others were eliminated. The results showed that both strictly certified survivors came exclusively from the chat-tuned branch of the model family. This heat map for the chat branch shows 2 coordinates where the models cleared the expanded F7 threshold. Each green sector represents a point of successful certification. The base branch heat map is a total void. Every coordinate tested for the base model resulted in 0% certification under the strict criteria. When refusal training is applied to a raw base model, the learned behavior overgeneralizes. The model begins refusing benign prompts because it has no foundational context for its new restrictions. Pre-existing chat tuning provides a foundational inductive bias. This shaping helps the model contextualize the new refusal weights and apply them more selectively. In this chart of over-refusal rates, the top 2 chat models remain comfortably below the dashed expanded F7 threshold. Further down, the base models consistently exceed that same threshold line. They are statistically incapable of maintaining selectivity under this training regime. A model's foundational structural alignment directly limits its capacity for selective refusal. The final checkpoint for the chat survivors was the F8 manual audit. This was a blind review of every harm response to search for residue like procedural steps or code. Both cells passed. They provided clean refusals and safe, non-operational alternatives without resorting to hedged compliance. However, clearing these safety gates does not guarantee that the models are highly intelligent or reliable. Looking at our feasible set map, both survivors sit directly on the interior boundary of the capability threshold. The raw capability scores were just 0.500 and 0.583. These models cleared the minimum survival requirements by only a few correct answers. In practical terms, these models were safe, but they frequently failed to correctly answer basic, harmless factual questions. This experiment focused on the mechanics of alignment rather than raw intelligence. It demonstrates that a model can be made safe even when its general competence is low. Passing strict certification proves a model can be selectively safe, but tells us very little about its general utility. The V03R3.3 experiment provides an existence proof for selective alignment. It does not establish a broad or stable region where these models can operate. Finding only 2 successful models out of 36 configurations is a marginal event that could easily be lost to statistical noise. The next requirement is the V03R3.3E run, which must replicate these specific coordinates across adjacent seeds to see if the success was a fluke. These results resemble a narrow mathematical coordinate that could easily vanish if the training conditions were slightly altered. If future replication across adjacent seeds fails, it would suggest that the feasible set for aligned models is even narrower than researchers currently hope. Selective refusal under frozen rules mathematically exists, though the current data suggests the feasible region is extremely narrow.